3-hour lecture. So the plan for these 3 hours is quite simple. What I would like is to present what really we are doing. Now it's not anymore, I think, at undergrad, which is getting much more into research and how we can use the numerical approaches that also we saw this morning, and doing research and trying to address problems that could range between hydraulic fracturing, slop stability, tunnel stability, but anything that involves the development of fracture. So the real goal is to try to see how we can combine experiments, numerical models, and what is the final goal is really to understand the behavior of complex, discontinuous, heterogeneous material. So it's not anymore limited to liquid, it's not anymore isotropic, linear elastic material, but now it's actually that material, that form. And what is actually important is that we need to understand how we can capture the transition from a continuous to a discontinuous fracture. That is really what needs to be done. And this is the type of processes that we would like to be able to model. So that's a reality. That is what is happening when, for some reason, a cliff collapsed. And we don't really want just to know what is this factor of safety, but the goal is also to see if that happens, what is going to be the results, and what we can do to actually prevent or reduce the impact of that failure. So, at the end, understanding fracturing is really the key. How the fracture propagates, when it starts, and what is the result of that process. So one of the problems that you have as an engineer, as a scientist, when using tools such those you used this morning, is that you are going to look at just the initiation of the fracture, the failure, but you have no clue what is happening after your system has failed. You can assess if it is in equilibrium, or very likely will lose its equilibrium, a slide for example, but it doesn't say anything on how that slope would result. What is going to happen after the failure? Is really failing completely, or just the crack is propagating up to the stabilization? So to do that, what we are using and we keep developing and trying to improve is a methodology, a technology if you wish, that try really to combine the aspect of continuum that could be really nicely modeled using the finite elements, and the fact that you can have your mag that breaks, so that is not a continuum piece anymore, but is made of parts, so it's a discontinuum, and can be captured through the discrete element algorithm. So what moves from one to the other is actually the fracture and fragmentation processes. And the way we are capturing that phenomenon is called the cohesive element approach. So if you like, it's just thinking about having your mesh. You understand what I mean for mesh? So you have your system, you discretize that in elements. I like triangles, let's use triangles. And then all those triangles are connected. So you can think about those triangles to be glued together. And that glue is your cohesive element. And if you stress, if you start stretching your mesh, at some point that glue can fail. So your cohesive element will fail. We stretch and ultimately will fail. And that is really what is the role of those cohesive elements. How glue can fail? They can fail in mode 1, tension, in mode 2, in shear, and in any way that could be the combination between the two. So it means it can fail in shear, tension, mode 1, in shear, or in a way where you have tensile component and a shear component. When your system is failed, your elements can interact and so they basically can bounce one against the other one, but when they try to slide, also they mobilize some sort of friction. And that friction is simply used as a Coulomb law. It's a fully dynamic solver. That means that at that point you need to integrate that in time. So you need to pick your time step. And the time step needs to be small, such as you can capture the behavior of your system. Plus, you can add a lot of additional physics, such as the thermal stress. So it means that your system will respond to change in temperature by dilating or contracting. You can add fluid. That means that it could be as a core pressure, means that you have a pressure within your system. And that is really typical of solid mechanics, pretty much. But you can also have fluid within the fractions. And that is, going back to yesterday, can be simply captured through a cubic fluid. And this coupling is fully coupled, means that when you change the stress, that stress has an influence both on the mechanical and the fluid part. What does it mean? If you have a fracture, you pressurize the fracture, that fluid will tend to open your system, your fractures. That means that you will apply a pressure to your to the surface of your crack. Will open, but because it opens, will increase the volume within the fracture. That means the pressure of your fluid will increase. So that means that it's fully coupled from one to the other. Okay? So that is really what we are going to use, and we're going to see a little bit more on the results. Before getting there, how this system is going to work. So, again, the name of the methodology is hybrid finite discrete element. And the acronym is FDEM. You will see FEMDEM, but recently it's more and more accepted that it's going to be called or named FDEM. That is really the acronym that is going to be used. So, the really key part that you need to understand is that you start start from a continuum and you ended up potentially with a discontinuum. And that is through a fracturing process. That fracturing process is really, at least the way it has been implemented, the code I'm going to present is a linear fraction mechanics and uses a cohesive element. How does it work? So you have your continuum. And you start trying to fail your medium. So what does it mean? A piece of paper. This is my continuum. And actually, I'm going to create a mesh made of two triangles. And these two triangles are actually connected by this cohesive element. So, and I can start stretching, I can bend it, I can apply stresses to my system. At some point, what is happening is actually I will apply enough stress, and that stress will result in a displacement that will be localized at that cohesive element. And what is happening is basically I'm pulling the two apart and I'm breaking. So now you can see that part of my system is broken and part is still connected. And this point where the fracture is propagating, now here, is really where you have the transition from a continuum to a discontinuum. So there are several ways that this fraction mechanic has been implemented. Some is looking at what is the stress of it. But start thinking that maybe it's not really the stress that is creating the failure, but actually it's the fact that I'm pulling apart, so I'm creating a concentrate displacement. I displace two sides of my body, I stretch them to a point that my body cannot accommodate that local displacement anymore and fails. And this happens in an area that is defined generally as fracture process zone, FPZ, fracture process zone. So numerically, what you're doing is basically this one. This fracture process zone is this yellow part. So it is accommodated to the cohesive elements that start stretching, and then at some point that the local displacement is so high that they cannot handle that. How do you transition from the continuum to the discontinuum? So it's basically this graph. So you can think about that your material is able to stand tensile stress, let's talk about tensile, equal to the tensile strength of the material, right? That's the definition. If the fracture is totally open, that fracture cannot stand any tension anymore. It's free. So you go from an intrinsic tensile strength of the material down to zero. And what is your assumption is that that process that brings you from the full tensile strength of the material to zero is actually continually dissipated along some length. And that length is actually defines the dimension of your fracture process. Okay? And is directly related to the elastic modulus of your material. Is it clear? Does it make sense? So basically, numerically, what you're doing, you're allowing your material to stretch. The more it stretches, the less cohesion can support, up to 0. So now, how does it work? Let's look at this graph. That graph is telling you that you start stretching. At some point, the material starts yielding. Well, I would like you to know that this is actually a stress, but this is not a strain. It's actually a displacement. So the idea is that you are not working on strain anymore, but on local displacement. And the whole idea is that it's not the stress that when you overcome a particular stress that you fail. It's actually that locally you need to displace your material far apart enough that will not, the bonding between the atoms there, the material will not stand anymore that displacement and will detach. So the reality, despite we are going to look at the stress for the initiation, in reality the fracture process zone will develop as a displacement criteria. So you need to displace the two sides of the future fracture enough that will break. So, and when you're displacing, you move from this point to that point. And this is basically the opening, the local displacement that you need to achieve so that the fracture will develop. And this sort of displacement is really where the fracture process zone happens. Okay? So now, what is the area underneath this curve? It's actually the energy that you dissipate in that particular process. This for mode 1. And you can do exactly the same for mode 2 for shear. So, what is, I hope you're going to retain is few things. One is that the transition from continuum to discontinuum at the end is it's basically a fraction. Numerically, the FDAM, as we have implemented that, uses cohesive fracture elements. And those cohesive fracture elements, they will fail based on energy and displacement. It's not a stress strain. It's a stress displacement. The nice thing is that everything is related to the energy that is consumed during the process. So basically what you need, and you can, is relate this particular fracturing to the fracture toughness, to the toughness of your material that you can measure. So it's not a non-physical property anymore, but it's a physical property. But at the same time, this is a micromechanical because we are looking at very local, small scale. Now, if ever you have a mixed mode, well, at that point you will have a component of shear, a component of tension, and basically is along where when you cut this envelope that you will develop the failure. So you are going to have a mixed mode with some sort of component of shear and some sort of component of tension. Are you following right now so far? Sort of? I hope so. in the elastic mode. The yielding is basically defined by 2 points. In mode 1, in tension, is basically the tensile strength of your material. The slope of this curve is nothing else than it's related to the GIAN modulus. And the slope of the mode 2 is basically related to the shear stiffness of your material. The yielding point in shear is defined by some sort of shear criteria. We are using the mode pull-up because it's the easiest way to use it. The shape of these curves are actually empirical and are derived from experiments where the scientists were able actually to see, to measure what was the stress and the displacement of a mode 1 fraction. How do you do that? You create a so rigid system that you actually can follow the loss in cohesion of your sample while you are applying a pure tension. Extremely difficult measurements. They did those measurements, and that is the empirical equation that has been developed following those tests. So at the end, numerically, what you have this glue, this cohesive element, starts stretching, and what you're going to measure is the aperture, the opening, so the mode 1 component, and the sliding, the shear component of that process. So this example is nothing else than a mixed mode development or stretching of your cohesive element. Okay? So again, the nice and neat part of this approach is that actually most of these properties can be related to measurements done in the lab. That's really nice because you don't have any more, or you reduce the uncertainty or the calibration, because you can directly use the properties measured in the lab with some attention to the fact that generally what you measure in the lab is a larger scale. So while here this value should be measured at really a very small scale. So there's a little bit of attention there, and that is where unfortunately the calibration of the model takes place. So you don't have you need to sort of check if the numbers you are using are correct or not, as we saw this morning. But if you can do that, you can sort of start looking and modeling systems that are extremely complex by using very simple equations. And what you can, you start reproducing fragmentation, primary fragmentation, failure, secondary fragmentation, flows of material, and so far. And these are not really easy. But you can see your fracture that is developing. You can see that your blocks are not anymore the same size, but really they change as a function of where they are in the process and how far are, for example, from the surface of failure. The other thing that we have been doing is to start looking at material such as shale, such as maybe limestones. Anyway, sedimentary materials where you do have stratification. So your material is not isotropic anymore, but it's transversely isotropic. That means that it behaves in a way, one plane, basically laminated. And the fracture and the behavior will drastically change if the fracture tries to go across those planes, perpendicular to those planes, or at some angle. So by how do you do that? Well, mathematically, we saw that you can define your transversely isotropic material by changing the elastic properties, and you have elastic properties along the plane, different perpendicular to the planes. So, but what we have been doing is the same approach for what it concerns also the cohesive element. So there will be elements that will be stronger if they need to cross the bending planes in this case, and definitely the cohesive elements will be weaker when they align with the cohesive elements. What does it mean? That by just looking at how those elements are aligned with respect to your bending planes that really are weak planes, you can capture the presence of those planes without having to explicitly measure for them. Okay? So that is okay. The other thing is that at the end you can add, we've been adding more and more physics, more and more coupling. For example, when you look at a fracture can flow. You can sort of inject a fracture, that fracture will, then the fluid will apply a pressure, the pressure will deform your body. Can actually some of the fluid go inside the pores and create pore pressure within your body. The fracture might not just develop as a plane, but to branch because of the heterogeneity that is presence of your rock, well, failing both one and two. But the other thing is that it's important to understand is that when you break, you consume energy, right? When you consume energy, some energy is basically dissipated. Others is actually transformed in kinetic energy, right? That kinetic energy is nothing else than energy that starts traveling, starts shaking your body. And everything is part, you don't prescribe for that, it's just part of the approach. You're just looking at how the nodes of each element will displace, and if it displaces, it means that there's some kinetic energy that will propagate. It means that you can have a seismic wave that starts propagating through the medium. What does it mean? It means that actually by just propagating a fracture, you allow also the shaking that is associated with that fracture to propagate through your medium. In other words, by just propagating a fracture, you are creating a very small seismic wave that will start propagating. And depending on what is the energy that is associated with that process, you can go from very small so-called acoustic emission up to a seismic event. That means that if I have, for example, very small fractures, and I compress that system it's a pre-existing fracture, and what happens, try to break. And generally what you develop are two wing cracks at the tip pretty much of your system. By doing that fracture, the system will release some energy, some loading, some strain energy is transformed, is consumed in fracture, and this is transformed in kinetic energy that start traveling. So it means that if I start looking at monitoring points around my system. What does it mean, monitoring points? I have one node, and I look how that node displaces with the time. And that is exactly what a seismographer does. So it means that at some point that point starts to vibrate. And that vibration is nothing else than your seismic signal that is recording at that given point. And this is exactly what we are being recording in America. It's very similar to what probably you saw in TV, maybe in your textbooks. Again, the interesting part, and I'm getting really excited, is that the fact that those signals actually carry information of the event that actually has caused those shaking. So by invert those signals, you can start looking at what type of events are associated with that shaking. You can start looking at if it is a more shear or more tensile components that are associated. And this is exactly what the seismologists, the geophysicists do when they look for, they analyze the seismic signal associated, for example, with earthquakes. So that's nice. But what it's telling us is something that without prescribing or solving for the wave equations within the system, the model is able to actually produce waves that carry a meaning. They carry the information of the initial failure that numerically happened. In other words, it appears that the physics that is implemented in the model is good enough to reproduce what we observe in the reality without doing anything specific. So what we are saying is that the model produces a response that emerges from basically the loading. We don't prescribe that a seismic wave should propagate, but that is the way the model works. That is the way Earth works. We don't prescribe that the surface shakes because of the earthquakes. It's just that's a process, that's a consequence. And the same thing here. So now, by using those very simple concept of elasticity of our elements, contact interaction, friction, and the cohesive models that are implemented on displacement and energy, what we can is actually reproduce phenomena that are much more complex. And all those emerges from very simple equations. So that is the interesting part. So you don't prescribe anymore the behavior, but you observe the behavior that emerges from the model. And what is that differentiate the one model from the others is nothing else than the boundary condition that you're going to apply. So what I mean is that if you have a rock, you tested the rock, right? So you tested 2 samples. One was under compressive uniaxial compression, and the other was under confined compression. so triaxial. So the only thing you change in between those two tests was just one thing. How you apply the confinement. The first one, there's no confinement. And the second, it was confined. Was the behavior the same? Was the way it was failed the same? Failed the same? No. One was a scatter, was all vertical cracks, and the other was nice, neat, sort of whatever, 18 degrees, 75 degrees, oriented fraction, right? What did you change then? Just the boundary conditions that rock was experiencing, and the behavior of the rock was totally different, right? So that was an emergent property, an emergent behavior. So, and then this FDAP is using basically the same thing. You change your boundary condition, your model will change the response. And that's the interesting part, because now you're not linked anymore to the equation, constitutive equation. You have very simple equations, and by just changing the boundary condition, everything changes. Don't prescribe the results. You just observe the results and then finally interpret them. So you can start looking at where it fails, what is the energy associated maybe with those events. So you can use exactly the same model, identical, same mesh, same pre-existing fractures, same well, and you change your boundary conditions. You go for same stress, no direction. Sigma 1 vertical, sigma 1 at 45 degrees, and sigma 1 horizontal. Nothing else. And then you pressurize the same increase in pressure that circular form. Are the fraction the same? No. It's completely different. The results, the outcome is totally different. So at the end, what we have a fraction that actually develops as function, or it really depends, the path, the trajectory, really depends on the stress state, your boundary condition that are applied to your model. Nothing changes between all these models but the stress state. That's it. The other thing is interesting is that these fractures actually start interacting with pre-existing joints, pre-existing cracks, pre-existing fractures that were in the model. They were all the same. But the end result is very different. And one thing that's really nice is that look at this crack. Arrives here, so it's going horizontal, and then at some point hits pre-existing cracks that are at weaker point, so it deviates, start to following those, and then at this particular point is actually start to realign with another pre-existing structure. And we didn't prescribe the system to behave in that way, but it did just for the simple reason that the stress was perturbed by the presence of that particular crack, and that was the result. So if you look at the same system, tunnel, under 25 megapascal vertical stress, 19.6 horizontal. If you assume that your system is continuum isotropic material, this is the type of failure that you observe. You run that in plaque, this is the type of plastic area that you will model. You start orienting, you start adding fractures and joints, while the failure is completely different. Again, nothing changes but just the presence of fractures. Again, you don't prescribe anything with respect to the behavior, but the only thing you do is really observe how your system reacts to the boundary conditions that you are applying. Okay? The thing is that that's nice, but where do we get the properties? Well, the more complicated is the model, the more complex is what you are doing, the more challenging is obtaining the input parameters. And specifically for the ARC-10, because of the system, the methodology is looking at a small scale, the best would be to measure the property, the elastic properties, for example, at a very small scale. And one way exists actually, and it's called indentation. You saw the indenter in the lab here. That is a classic macroscopic indenter. You can actually make it small. And you can start probing your material at the single grain scale. So now you don't have anymore the elastic modulus of your sample, but you are going to have a distribution of GIAN modulus that are associated with the single grains. That may be what you want to start using. And of course, you start using characterize the material at a larger scale. So this is the example of what basically the indentation has. As a tip that probe your material, deforms it up to a point, and when the material, and then release the force, and the material rebound, and that you measure what is the elastic modulus of that rebound. That's pretty much what it is. And then, at the same time, you can see under the microscope those small, very small indentation that we have created. At the same time, you can also drive cracks through the indentation that will help you to estimate what is the fracture toughness of that particular material. And that is what you need to fully constrain the energy associated with the fracturing process for the crazy level. So by doing these tests that are not the classical tests that we saw during this course, but it's a little bit more advanced, you can start constraining more and more what are the input for this type of biomechanical models. The other thing that's interesting is that rock is not homogeneous, it is highly heterogeneous. So what you can is do this measurement not just at one single point, but on a grid, for example. So at each point here of the grid, you're going to measure your fracture toughness and your elastic modulus. That means that you don't have a one number anymore, but you start having distributions. And those distributions can be associated to the component of your problem. And at that point, you can start thinking about how I can use, instead of doing the indentation as the system here, you can do micro indentation. So now you have not one phase anymore, we have several phases, and then you decide how to homogenize them if your element is larger. And that way, you bring the micromechanical behavior into your input parameters. And you're going to be able to capture more and more the heterogeneity of your material. That could be a rock, it could be a cement, a concrete. And ultimately, what you're going to do, you run your Brazilian test, and you run your equivalent Brazilian test where you try to capture, from a statistical point of view, the contents of the different phases, aggregates, phase in this case, of the material. And what you want is at the end to try to match what you measure microscopically in the lab with what you measure numerically. What you are aiming is to have the same GIAN modulus, of course the same strength. So that means that also the displacement, the strain at the peak will be the same. If you're happy with that, you can do the same in the compressive test. And again, same thing. What you want is to match the behavior in the lab, the behavior that you observe. Now, this is just one representation. You should do that with several different distributions, just to make sure that you capture the heterogeneity that you have in your sample. Once that will be close enough and comparable to what you observe in the lab, well, now you can start doing a little bit more analysis. So what are good these tools for? What are they made? Well, the fact that you can reproduce emergent properties, and if you are able to really calibrate your system, well, it means that you can numerically start investigating how your system responds to changing in boundary conditions. And you can have very nice and neat behaviors. So it means that, for example, I can look at how my system changes its response by increasing the confinement, and you get what? You get a change in behavior. You go from a brittle to sort of a more tactile response, and you compare that to your lab results. You are happy. At that point, you can start looking a little bit more. You can start looking at how it fails. What is actually the process that leads you to those curves? You start looking at what is the effect, for example, of different grains, the grain size, the distribution, or maybe even the clustering those grains on your strength, but also on the fracturing process, on the path the fracture will follow. And of course, you can try to use really advanced laboratory tools such as the X-ray CT that makes your system transparent. You can start seeing how a granite sample, for example, in this case, fails under triaxial or uniaxial state. And what you can start looking at is what is the effect of the presence, for example, biotite with respect to the trajectory of your system. By comparing your numerical model to the experiments, and once that you are confident enough on the results, what you can start looking is really the process. Try to understand what is the fundamental process that actually leads to the final results, the failure. What is important? Because at the end, if you do understand what is the process, you really have a full understanding of your behavior of the material. And you can start understanding much better this type of system. You can start understanding a bit small thing. What I wanted is actually this one. Sorry. I made a mistake on. You can start looking and understanding what is happening to your process. You can start looking at trying to reproduce what is happening, why the fracture is developing there during a shear test. You can start understanding what is the component of each, the influence of each single component on the final process. So, I think we should stop here, but I want to close with showing you a few really type of experiments you start thinking about, because the technology allows you, and how you can couple that with really advanced numerical modeling such as FDEM. And by doing that, the value is not only that you get the results that matches what you observe in the lab, but you have a tool to back analyze and really understand what are the reasons that will lead you to those failures. And by understanding, when you understand the process, you can, and you have a tool that is able to reproduce numerically data, you can start changing your assumptions and start thinking about experimenting what you could do to prevent or to increase those failures, depending really what is the goal. You want to have a better fragmentation in mining? Well, I want to see what could be the change in boundary conditioning need to apply to my rock class to actually obtain that. What is the influence of joint sets during blasting? Well, I could start investigating that. I want to design a new tool for, I don't know, drilling. Again, I can start looking at what is the process or the impact or the weight of the bit I could apply to increase performance of my process. Just ideas. But all depends on how your model can capture the physics and how you can really then investigate or calibrate that model and reproduce that, and then it becomes a really nice tool to improve, to engineer your process. And at the end, what you can is start looking at the evolution. You're not looking anymore at one fracture phase. You look at what is the evolution of that process. You can do that in the lab. You can start observing your system while it's failing. And then you can do the same numerically. And what you really obtain are a few things that are really nice. You can start shearing your system. You can see the contact changes, some asperity breaks, some stress wave are propagating, and you can start having a feeling of what is the process that will lead to the white patches that you actually saw on those, that sample during the reaction, right? So I skipped a few things. But what I want to see is that numerically you can start seeing that one failure might create a wave that actually go and trigger a second failure, the failure of second asperities, and that is basically a dynamic trigger event. This is small scale, but then you can, from what you learn, you can start investigating what a failure some place away from a tunnel in a tunnel that is in a highly stressed condition could lead to actually a rock burst. I'm not saying that for sure is happening, but there are conditions where that might happen, and you need to be aware of that. That is, for example, a very simple case would be that you have a highly stressed mine. The drift is really close to failure, so your stress at the around the tunnel at the surface is really close to failure, and you blast somewhere away from your drift. What is happening is that the strong stress wave is going to increase the loading, basically loads an already close to failure system, and that will trigger brittle explosive failure such as a rock burst. And that is things that you can start investigating. And well, this is actually a cool system. It's just that what you can just start thinking about better, or looking at what is the fragmentation associated, for example, with plastic. You can see what is the change in the results if you change the delays in between the different holes. What is the influence of actually having a core detonation versus the electronic detonators that are much more precise? Is something that we can do better to actually have a much more controlled fragmentation during our plastic. All these are applications of new technologies, and those technologies do not need to prescribe actually the results, but they just need to make sure that the system is correctly calibrated, and let your system to just work. And today we stop here. Any questions? Overwhelmed. And tomorrow will be worse. Much worse. So, but my point is that at the end, in these few days, we went through from the basic stress strain, very boring things. Basic because you need to understand what are the beginning. And then we moved to the lab. We tried to see what is the influence and how we can describe the fractures. Because fracture is really what we are dealing rocks all the time. And now we start looking at how we can bring all together into complex numerical models that will help to actually understand what is happening. But the more the system is complicated, is complex, the more difficult it is to understand if the results are correct or wrong. How to calibrate it. And that's really the challenge, is the more complicated the system becomes, the more difficult it is to understand if it's correct or wrong. And that is where experience comes, where studying comes, and but that's the future actually. So you don't do the calculation anymore with a calculator. I don't even know if you own a calculator anymore. Probably you use your cell phone. So you don't take pictures anymore with a camera. I don't know how many of you even own a camera. So that's the point. Right now we are moving towards a much more complex and complicated system. And those systems right now, I think, are moving towards the FDEM approach, where you can combine both the finite element, the discrete element, the fracture mechanics. But then is how do you calibrate that? What do you measure? How do you model that? What are the parameters? What are the timestamps?